Welcome to section 3, Optionals. In this section, we're going to take a look at what an optional T is, STD optional T's interface and semantics, and example use cases for optionals. Let's begin with video. What is an optional? In this video, we're going to take a look at what an optional represents, a possible implementation of optional, and a comparison between optionals and pointers. Let's begin by trying to find the meaning of optional of T. An optional T can fundamentally be in two states. It can be set, which means that the optional contains an instance of T, or it can be unset, which means that the optional does not contain any instance of T, so it is empty. An optional represents a value that may or may not be present. It has value semantics and doesn't use any dynamic allocation. If you think about it, the size of an optional of T is slightly bigger than the size of T. This means that the instance is stored inside the optional plus a flag to check whether or not the optional is currently empty. Here's an example how you can use STD optional. In the first line, we are creating an STD optional of int called O, and this is initially unset because the default constructor of an optional creates an empty optional. To check that, we can assert that it has no value by invoking the hasValue member function. If we use the assignment operator with 15, we are saying that we want to create a value of int inside the optional with value 15, and O becomes set. We can then assert that the value of the optional is present and that the value is 15. Finally, if we want to make the optional empty again, we have a few options. In this case, I'm using assignment with the special STD nullopt object, which represents an empty optional, which makes the optional empty again, and we can assert that by checking that hasValue is equal to false. Let's keep trying to understand the meaning of optional. An intuition, since you're not familiar with variants, is that optional is similar to a variant of T or nothing. Additionally, optional can properly model functions that can fail where no extra error information is required. So it's a function that can either return a result or no result. Similarly, they can model the expected absence of a result. In this case, searching in a container might sometimes return nothing, and optional is a great way of modeling that. They can also model non-mandatory data members and arguments, and finally, they can be used to control the construction and destruction of an object. In this case, I say defer here because it's the most common use case for sticking something inside an option. In this case, I say deferred here because it's the most common use case for placing an object inside an optional with the intention of controlling its lifetime. Here's an example of a function signature which benefits from optional. Imagine a function called parse string to int, which given a string returns an int parsing the string. Sometimes the string might be invalid and cannot be parsed. So what we can do is return an optional of int instead of a simple int, which will be unset if the string wasn't able to be parsed, or which will be set with the value that was parsed otherwise. Another example is finding a substring inside a pass string. In this case, we will return the index if we find a match by placing it inside the optional, but if there is no such match, we can simply return an unset optional. The benefit of this kind of interface is that, similarly to variant, the caller knows that this can fail from the signature of the function, and the caller is forced to check the status of the optional in order to get expected behavior. Optionals can also be useful inside data structures. In this case, you're trying to model a person, which will always have a name, but he might or she might have or not have an employer. So you could say STD optional of employer to represent that empty state. And this is an example of when you would want to use optional to control the lifetime of an object. Imagine that you have some sort of microservice architecture and you're writing the class for this service, and you have a complicated component called request processor that maybe starts its own thread, does some initialization, and you want to prevent that component from being constructed until you do your own initialization for the service. So what you can do is you can place it inside an optional, then in your constructor you will have your initialization steps, and finally you can initialize it inside the optional. In this case, I'm using the inplace member function, which will take any amount of arguments and pass them to the constructor of the instance inside the optional, but we will dive into that later. The benefit here is that request processor is a RAI class, so it kind of manages its own resources, and we still retain that safety and convenience, but we can also defer its construction. Let's now take a look at the memory layout of optional T. Conceptually, optional T is just some storage for a T instance and a boolean that keeps track of whether or not the optional is set. If you imagine a very, very naive implementation, you would have something like a template class called optional that contains an std align storage with the size of T and alignment of T, and a boolean that is defaulted to false. If you've never seen align storage before, it's a C++ 14 introduction in the case of the _t type alias, which allows you to create uninitialized memory storage in place on the stack with a particular size and alignment. And if the size of alignment both match a specific type, it is safe and guaranteed that you can instantiate a type inside that storage and it will behave consistently. If you think about it, this means that there is no dynamic allocation at all, and that you can have value semantics in optional T quite easily. It's an inexpensive abstraction compared to something like a smart pointer, and it's potentially more cache friendly because it's contiguous in memory. So if you like a vector of optionals and you're going to iterate over it a lot of times, it's going to be faster than a vector of unique pointer, as an example. So my guideline is that optional should be your first choice when you want to either represent the possible absence of a value of parameter, model a function that can fail or return nothing, or manually want to control the lifetime of an object. Let's take a closer look at the comparison between optional and smart pointers. So both optional T and unique pointer of T can be used to control the lifetime of an object or represent the absence of a T instance, since unique pointer has a null state. However, if you only want to do that, using a smart pointer has several drawbacks. The most important one, in my opinion, is that you lose the value semantics, because you now have this indirection on the heap, and you need to make sure that your type supports deep cloning semantics if you want them. You also have overhead due to dynamic allocation, and overhead due to indirection. This might be a performance issue if you're using unique pointer or any sort of smart pointer in a hot path of your program. It's also useful to compare optional to a raw pointer. T star can be used to represent a potentially null reference to an existing T instance. Remember that in modern C++, a raw pointer should never have ownership semantics. Not all optional implementations support optional of tref, which means a reference that can be or not be there. And especially the standard library implementation of optional that's introduced in C++ 17 does not support references. It is therefore idiomatic and recommended to use a raw pointer to T to return or accept a reference that might be null. So as long as T never owns the memory it points to, feel free to use it to represent something that points to an object which might exist or not exist. Remember that manual memory management is unsafe and superseded by smart pointers, so never use raw, new, and delete when dealing with raw pointers. If your implementation supports optional tref, you can use it to represent a non-owning nullable reference to T. As an example, boost optional supports references. This kind of non-owning nullable reference can sometimes be more type safe than T star, because there are some very useful abstractions on top of optional that can help you visit it or concatenate operations one after another. Otherwise, I still think that a raw pointer is fine, but you must explicitly remember to check full nar pointer before accessing it.